Shall we start now?
Okay, ma'am, we can.
Okay. So I welcome you all to this session, and also I welcome our resource person, Professor Vishnu Nambudiri, and I hand over to this session to you.
Thank you, ma'am. Good morning to all of you. Till yesterday, we were discussing various things related to computing mathematics using Python programming language, and we have seen several modules available in Python programming language for performing the computations. So, day before yesterday, we started discussing something related to curve fitting, least square curve fitting, which essentially means that suppose that we are given data points like x, y, obtained through some experiment or using some function. We know certain functions. We were trying to find out a straight line initially that will be as close to these data points as possible, in the sense that the distance from the points on the line to these data points differ. The square of the sum of the distances differ by the least possible value, that we are setting. That's what the least square curve fitting is. After that, what we were trying to do is, I told that if your data is well behaved, then we can assume that the data that we have corresponds to a function which is differentiable, infinitely differentiable. Therefore, there is a polynomial approximation. Yesterday or day before yesterday, I think Professor Raji already pointed out that for the function to have a polynomial representation, it's not necessary to have. It's not necessary that the function should be differentiable. It's enough that it's continuous by Weierstrass approximation. That's correct. That's actually correct. But Taylor series approximation actually gives you a concrete way to construct such a polynomial if such a thing is existing. But since we don't have a polynomial in our hand, Weierstrass approximation is good enough. So the essence of the discussion is that since we are sure that if the function is continuous, forget about differentiability. If the function is continuous, then we have a polynomial representation, and therefore it is natural that we hope to fit our data into a polynomial. Okay, we hope. I'm not saying that we will be able to. We hope to fit our polynomial. We hope to fit our data into some polynomial curve. Now, the polynomial curve. The problem is that polynomial curves are of different degrees. It can be a degree one polynomial, linear polynomial, can be quadratic, it can be a 3-degree polynomial. All these things are possible. Now, after discussing how to construct a linear fitting, least square fitting curve as a line, now we are going to see how to fit the given data into a polynomial of arbitrary degree. Okay, the degree that we are deciding. So for that, what I told yesterday is that we require a little bit of linear algebra related things for computing the least fitting polynomial with arbitrary degree. So we have covered almost all the requirements that is required for constructing the polynomial fit. Therefore, we are going to discuss the least square fit in the case of a polynomial. So we are going to fit the data into a polynomial of arbitrary degree. So we can keep on changing the degree, and we can see that how the data is, how the curve is actually passing through the polynomial that already given data points. So the main discussion that we are going to undertake today is to fit the given data into a polynomial of arbitrary degree. Okay, let me start sharing my screen in Spider. And if you are trying in Google Colab, you can please open your windows. I will share the Google document link also with you. So the Google document link. Here it is. Yeah, even before going into that spider window, I would like to show the computations that we are going to perform. This computations, this formula, the metrics that we are going to construct is taken from the Mathematica website of Wolfram. I'll share that screen first. So this is what this is not actually from Wolfram website. This data is this the computation explained here is taken from the Wolfram website here, Wolfram Math World website. It's a very famous website for this is Wolfram is actually the provider of one of the most efficient software in computing, especially in the case of pure mathematics. MATLAB is actually supposed to be a software which helps mostly engineers. Mathematica is not like that. Mathematica is one of the software that helps Mathematica, and at the same time, Maple is also there. These two are not free software. Mathematica, Maple, these two are highly priced software. Alternatively, if you want, we can use Sage Mathematics or Python associated with all the required modules that we had discussed so far. So Python is actually, in some sense, an open source replacement of Mathematica, Maple, such softwares, and of course MATLAB also. But the thing is that you need to include the too many modules into Python for using with your area of study or your area of research. But Mathematica is not like that. Most of the modules are already built into that, and not only that, it has a decent documentation, and not only that, further the commands are all standardized and consistent. But the problem with Python, the problem with Sage is that being open source, it's developed by many people. So the style of the commands may differ from person to person. For the same kind of functionality, there can be more than one command. All these kinds are possible in Python. So confusions are quite possible in Python and Sage mathematics. But such a confusion is very less, is what I understand in Mathematica. I had used Mathematica, but I had not used Maple much. But what I think is, what I have seen is that Maple is one of the most powerful software even compared to Mathematica. Okay, but I have not used Maple, but I have used Mathematica and Sage Mathematics, and of course Python also. So this is the least square fitting to a polynomial explanation. There are a lot of things. We are not going to discuss any of these things. We can I can probably share this link with you so that you can have a look if you would like to even later. If you want to get a better understanding of the theory behind all these things, you can probably have a look at this link, Mathematica page link, Math World page link. So essentially, we are going to fit into a polynomial y equal to, you can probably see that I am increasing the size of that. Essentially, we are going to fit the given data into a polynomial of the form a0 plus a1x plus etc. ak x raised to k. That's a kth degree polynomial. So in that case, finally what happens is that we need to find out the coefficients a0, a1, etc. ak. This is the only thing from this is the only thing that we are supposed to do from the computational point of view. The theoretical point of view, it's not like that. You need to understand all these things. Okay, the how we are arriving at this and how the computation is performed and what is how do we arrive at the formula for computing a0 up to ak. All these things we need to find out if we want to really understand the theory behind that thing. But we are not going into that. The theory behind arriving at the formula for a0, a1, etc. to ak is not very difficult. We can of course go through that. We can read that. Some partial differentiation is used, and some extra computations are used for deriving those formulas. And finally, it leads to all these computations lead to a system of equations of this form: a0, a1, etc. And to solve this system of equations in the matrix form, if we express, it looks like this: n sigma xi square etc. up to sigma xi raised to k, and in the second row sigma xi square sigma xi raised to k plus 1. In the third row, you can guess that it's going to be sigma xi cube sigma xi raised to 4 etc. up to sigma xi raised to k plus 2 etc. Coming down, you will be getting sigma. This is the how many rows are there, how many columns are there, how many rows and how many columns. You can see that here we are starting with n, because sigma xi to the power 0. Okay, you can consider this n to be sigma xi to the power 0. Xi to the power 0, taking it to be equal to 1. Therefore, this is starting from 0th power up to kth power. So you have k plus 1 columns. And if you come down, once again, starting from sigma xi raised to 0 to sigma xi to the power k. So k plus 1 rows are here. Therefore, this is a k plus 1 into k plus 1 matrix. And we have to find solutions of, we have to find coefficients, number of coefficients we have to find is also k plus 1. On the right side, we have sigma yi, sigma xi yi, etc. sigma xi raised to k yi. This is also a matrix. This is actually a column matrix consisting of k plus 1 rows. Okay, so we are dealing with square matrix and two column matrices. To solve this, we know that the best thing that we can do is that, provided that the left side is see, if you want to construct a unique polynomial, this has to be, left side has to be invertible. So below that, we can actually see that this is a one-to-one matrix. We can also obtain the matrix of least square by writing something, etc., etc. So essentially, what we want to find is, we want to find the inverse of this matrix, n sigma xi, etc., sigma xi raised to k, etc., etc. We need to find the inverse of this matrix, so that a naught, a1, etc., ak will become equal to inverse of that matrix into the right side. Okay, inverse of the matrix in right side, because if you operate with the inverse of the left side matrix on both sides, you will get a naught, a1, a2, etc. up to ak. That's the thing that we have to find. So our task is to compute this sigma xi, sigma xi square, etc. And on the right side, we need to compute sigma yi, sigma xi yi, etc., sigma xi raised to k yi. This is what we are trying to do. After that, we will construct the polynomial y. We will try to plot it through the data given to us, and we will see if it's fitting or not. Okay, I hope that what I'm trying to say is clear to all of you. So I am moving to the spider screen and starting to write. If you want to have a look at these things, you can just open the Mathematica link, the Math World link that I have provided to you in the chat box, in the message box. You can have a look at the equation. I'm not going to show that equation again. I'm just going to spider it. Okay. You may have a look at that for a minute, so that you can understand that what exactly we are trying to do. So we are trying to compute this a naught up to ak. Not that there is actually a parabola fitting also in least square curve fitting, but parabola fitting is essentially going to become this what you call curve fitting itself, because parabola is also, it's also a quadratic polynomial. But of course, parabola has certain what do you call, some relation between the coefficients exists there. So there can be a little bit of variations here and there. But I think if you understand the polynomial fitting, that's good enough for most of the usual curves. And we will try to see the exponential function fitting also after that. That's also very easy once you understand this polynomial fitting. And with that, we will complete the least square fitting topic. Okay, let me go to the spider window. In Google document, I have not pasted anything. I'm just going to start. See, after typing only, I will copy and paste. I have not started anything to type. Okay, let me share the spider window. Here it is. So yesterday it was 57th program. Now we are moving to 58. Polynomial fit.py. We put the program name like that. So the very first thing that we need is data points. Okay, I'm going to take an example from the same page, not the same page. Initially, I had shown you one page. After that, I started showing you the Mathematica page. I'm going to take an example from the initial page that I have shown to you, so that we can, I can show you later that if our computations are matching with whatever is given there. I'm going to make use of that example in which x data and y data are given to be something. Okay, let me take the x data. X is equal to, oh, we have to import it. Importing. NP array, so that all the computations can be carried out easily. The values I'm copying are -3, -2, -1, So these are the values. So minus 3, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, this is in the increasing order. So these are the x values. Correspondingly, the y values are again numerical Python array. There are 8 values correspondingly. Sorry, 6 values correspondingly: 0 0.8, 0 0.4, 0 0.2, 1, 0. So the n in our case is length of x or y, whatever. Now, what are the things that we need to compute? We need to compute sigma x to the power. It depends upon the degree of the polynomial that we want to fit into. Okay, it depends upon the dimension of that matrix depends upon the degree of the polynomial to which we are trying to fit. For example, if you are trying to fit into a 3-degree polynomial, we need to take degree to be equal to 3. And suppose that we are going to fit into a second-degree polynomial, quadratic polynomial. Okay, suppose that we are going to fit into a second-degree polynomial. So k equal to 2. A quadratic polynomial. So in such a case, we know that what are the things that we need to compute? We need to start computing from sigma xi square, etc., up to sigma xi to the power k. That means sigma xi square. These are the two things that we need to compute. So we need both these things, and after that, we need to compute all the sigma yi, sigma xi yi, and sigma xi square yi. These are the things that we need to compute. Okay, so the matrix essentially consists of starting with n. N is nothing but it's sigma xi to the power 0, but xi to the power 0 we cannot give into numerical Python because a variable 2 or anything to the power 0 that may create some trouble for us. So we are not going into do that. We need all the columns. Okay, we need all the columns first of all. So for getting the columns, okay, we can. How do we get the columns? So to get the columns, instead of computing a sigma xi square, sigma xi cube, etc., several times, we can instead of that, see, in numerical Python, the array, the matrix is defined by means of defining the what do you call it, the rows. So we need to define the rows. We need to find out the rows. The rows are n sigma xi square, etc., sigma xi raised to k. Second is sigma xi square, etc., up to sigma xi raised to k plus 1, which is 3. So we need to find, yeah, it is not actually 3. We need to go up to finding sigma xi to the power 2k, which is sigma xi to the power 4. Okay, we require all these things. So let us try to find all these powers. X powers we will simply form. X power sum, let us call, and here we will save all these xi, sigma xi square, and from there we can take all those things into for creating the rows. I think that's much quicker, because if you keep on performing the additions, that may slow down the program. So it is not actually computationally effective. So let us compute all the powers simultaneously and take the pieces in such a way that those pieces will fit into the matrix that we want to construct. So x power sum, we are going to form all the sums. So what are the sums we have to form? Sigma xi we require. So sum, straight away we take sum of x, that is sigma xi. Now what do we require? We will see that if we can automate this further. Sum of x square is required. So sum of x cube is required. Up to 2k we have to go. Sum of x to the power 4 is required. Or otherwise, what we are trying to do here is sum of, what we are trying to do here is x to the power I, right, for I in range from where to where we have to do 1 to 2k plus 1, because we want to take 2k also. 1 to 2k plus 1, because remember that range command always takes left closed and right open. So 1 will be included, 2k plus 1 will not be included, but 2k will be included. So this is essentially we want. So that's it. This is not required. What's the problem here? Oh, 2k plus 1. That's the problem. Okay. 2 star k plus 1. X to the power I for I in range 1, 2k plus 1. Fine. Let us print it and see. So what are the values coming? Remember that this is the sum. So minus 3, minus 2, minus 1. So minus 3, minus 1 cancels with 3 and 1. So minus 2 is remaining. Minus 2 plus 1, minus 1, minus 1, minus 1 point, minus 1, sorry. Minus 3 plus 3, 1, minus 1 cancel. So minus 2 is remaining. Minus 0.2 is remaining. So that's correct. So the other source should be correct. Okay, let me update up to here in the Google document. So updated. The Google document is updated. Okay, now we require what type of matrix is required? We require a k plus 1 into k plus 1 matrix. Okay. It's a k plus 1 square matrix. So how do we do that? How do we get the k plus 1 square matrix? That's the next question. Remember that for what essentially we have to do is that the first row is going to be, so k plus 1 means 3 equal to 3. So 3 by 3 matrix is required. The first row is going to be n. N is now length of x, which is which is 6. So the first entry in that matrix is going to be equal to 6. After that, it's going to be equal to minus 2.2. After that, it is 24.04. Next row is going to be minus 2.2, 24.04, minus 8. And the last row is going to be 24.04, minus 8, 180. So every time we need to shift. Okay, every time we need to shift. So maybe we can, what we can do is, we can actually push this to this x power sum, we can push this n also, so that we can easily get, we need to take 3 at a time. So three elements from the beginning, 3 elements, second 3 elements, third 3 elements, like that we can keep on taking. Okay, let us push n also into this. So x power sum now consists of sigma xi square, sigma xi cube. And sigma xi raised to 4 is also there. Xi and 2k plus 1. How much is 2k plus 1? 2k is how much? It's 4. So xi square, xi cube, xi raised to 4. Yes, x up to xi raised to 4 is there. So let us push this, what you call n also into this. I don't know. It's a list, so we can insert. At 0, what should we insert? N. So it will become this much. Okay, so the rows are to be constructed from this x powers. I hope that you understood what exactly I did. I inserted this n to the first position of this array, so that we can take the first row of the matrix that we want to construct to be the 0th element, first element, second element. Second row will be 1, 2, 3. Third element will be 2, 3, 4. Okay, this is what essentially we want. Now, constructing the matrix. Uh, Maybe we can call it to be coefficient matrix. Now, how do we do that? Maybe we can initially take it to be a list so that the list is easy to handle, and after that we can convert it into an ND array, an NP array. So 0 to we can keep on shifting, right? That's what essentially we want. For how many times we need to shift? So take the elements we need to take is 0, 1, 2, and after that 1, 2, 3 from x power sum, and after that 2, 3, 4. Okay, 0, 1, 2, 3, 4. So this is what we actually want. Zeroth element, first element, second element, one, first element, second element, third element. So in this particular case, since we have only this is a quadratic polynomial fit, this can be actually done manually. So we can take x power some 0, x power some 1, x power some 2, x power, and after that x power 1, x power 2, x power 3, x power some 2, x power. But if the polynomial size is increasing, we should not go into that. So what I'm saying is one a quick way to do this is just take a list of lists like x power some 0. So this is what essentially we want. 2, 3. So the first row is over, and after that 1. Oh, sorry, one is missing from this. 1, 2. Now it is 1, 2, 3, 2, 3. So that is done. Now 2, 3, 4. 2, 3. I'm just pasting 4. And I can convert this into an ND array after that. Let us see this in action. So it becomes 6 minus 2, 24, minus 2, 24, 8, 24, minus 8, 180. So this is exactly what we want, and now we can convert this into an NP array. So this is one way. But as I told, if we have too many, if the degree is much more doing this manually by taking each and every row like this, it's going to be somewhat difficult. So instead of that, we should try to do something to automate it. So how do we do that? We can just take it to be equal to list comprehension probably will again work. So let us take this to be I. Next is I plus 1, and we arrange this I. Next is I plus 2. You see this? Initially we set this I to be equal to 0. Therefore, I plus 1 will automatically become 1. This will become 2. So let's do that. For I in range. So we need 0, 1 and 2 to be the first elements. I in range 0, 1, 2. So we need to take up to 3. So this 3 is coming from where? This 3 is coming from where? Basically because why we have 3 here? Because we have k is equal to 2, right? So k is equal to 2 means that we need to go up to xi to the power k, which is k plus 1 elements are there. So for range k, if you go up to k plus 1, yeah, that's fine. Sorry, k plus 1. Are we going to get exactly the same thing? Let's see. Coefficient matrix is here. Minus 6, 2.2, 24, minus 2, 24. Yeah, that's perfect. Now convert this into an NP array. So the coefficient matrix is ready. See that we can do it manually, or we can do it. We can use the full power of Python to do all these things, to automate these things. Now, the good thing with this is that if you change this k to something else, still this code will work. Okay, but if you manually put here range 3, then the problem is that with every degree polynomial, you need to change this. Here, you don't have that problem. Okay, now everything is quite simple, quite straightforward. Oh no, so sorry. The right side thing also we need to compute. The right side thing is that sigma of yi, sigma xi yi, etc. up to sigma xi to the power k yi. Okay, so that also needs to be computed. What do we call that matrix? The right side matrix, we call that to be the constant matrix. Or what is it exactly? I don't remember the name of that we usually call. Let me take that to be the constant, or sometimes the constraint matrix also we may say. So what do we need to compute? There we need to compute sigma yi, sigma xi to the power yi. So yi part is constant, xi only the power is varying. So let us again use list comprehension. Sum of yi, sorry, yi doesn't make any sense. What is yi? It's y. Sum of y, this is, sorry, even this is not correct. Sum, this is a function, so you should put it in a bracket. Next is sum of x2, sum of x star y is what you require, xy. Next is sum of x square star y, x square y. So up to xi to the power k. So that's it. So even here, even in this case, how do we perform the computation otherwise? Automatically, without using the fact that k is equal to 2. So the only difficulty here is that x to the power 0. I don't know what this x to the power 0 is going to be. Okay, let me just try. Print x to the power 0. Will it be taken as 1? If it's being taken as 1, then we can safely use straight away that x to the power 0. Yeah, therefore x to the power 0 is anyway working. So it doesn't matter. You can use that. So we can straight away use here it is x to the power 0 star. So instead of that, as in the previous case, what we can do is we can use list comprehension once again. Sum of x to the power I star y for I in range k plus 1. That's it. The matrix is 2.4 minus 4, 11. Yeah, it matches with the computation that's available in that web page. So I'm taking this example from. I'll just share with you. This example is taken from this page. So everything is ready. the constant matrix is there, coefficient matrix is there. Now we need to just compute a naught, a1, etc. So for getting a naught, a1, etc., what do we need is we need to, sorry, this is not necessary. This is the manual computation and this is the automatic computation. So compute up to here. Now what do we need? We need to find the inverse, right? We need to find the inverse of the coefficient matrix. Provided that the determinant is non-zero, we can try to make sure if that is actually the case. But how did we find the inverse? The determinant is inverse is found using determinant is found using NP linear Rollins curve. Okay. Let's try to see the determinant first. NP. A determinant is non-zero, so inverse definitely exists, and I believe that the inverse is to exist because otherwise the problem may not have a proper solution. So I think by the theory itself it should exist is what I think. Now finding the inverse. The inverse is here. Inverse is here in this matrix. Now we need to compute the product of the coefficient matrix with the constant matrix so that we will get the final solution. Coefficients is equal to coefficient matrix inverse. We need to use NP dot coefficient matrix inverse with constant matrix. A naught to AK. Okay, let me just compare with the solution available here. 0.229 fine, minus 1628 fine, 0.27. If you check that web page that I have shared with you, you can see that the coefficients are exactly the same as this. A naught to AK, even this we can A naught to, we can format if you like. Format A naught to A2. So the polynomial is y is equal to, so if you want to show the polynomial as a polynomial, you need symbolic Python. Oh, you should not use x here probably. Maybe we can change this x to x data. And y to y data. X equal to symbol x. So the polynomial finally is, what do you need? You have a naught, so 0 to k, right? 0 to k, we need to multiply a naught, a1, a2, etc. You need to a0, a1, a2. You should multiply with x0, x to the power 0, x to the power 1, x to the power 2. That's it. So the curve is the polynomial is. So you need to sum. What are the things that you need to sum? Okay, the coefficients you have stored here, and coefficients with I don't know whether the sum will work or not. The coefficients and x to the power x powers. Let us take x powers 2, x to the power. Okay, this is only a symbolic representation anyhow. That doesn't make much sense because we are going to use only the coefficients, but only to show that what exactly the polynomial is. We're trying to do that. X to the power I. That what I'm wondering is whether with the symbolic Python this I will work or not. For I in range, so you require up to uh, k plus 1 because we need a degree 3, degree 2 polynomial. I don't know whether this will work. I suspect. Or maybe otherwise we can sum. Let us see at least if this is working. X to the power I for I in range k plus 1. What's the problem here? So 1x x square, that's quite fine. So there is no problem there. Now to show the polynomial, right? Y equal to, to show the polynomial, what should we do? We wanted to sum of coefficients star x powers. I'm not sure whether this will work. That's anyway working. 0.27 x. Where is it? Yeah, 0.27 is x square. This is x and 2290. Are the coefficients correct? Yeah, that's correct. So you are getting the polynomial to be this. Now trying to fit the data. Trying to show the plot. Import matplotlib, pyplot, as plt, plt plot x data, y data. After that plt plot. So we have a polynomial here. Let us try to plot the polynomial. So the polynomial values we require x. Polynomial values are x values are exactly the same. There is no difference. Maybe we can get to get a smooth curve. Let us take the x values to be from where to where the x values are here. It's from -3 to 3. So let us take -3 to 3. np dot linear space -3 to 3, some 20 points, and y values correspondingly. We can take np, or we need to just substitute y dot subs. So what to substitute? X to be substituted. X a for a in x value. So to this polynomial, we are substituting at the place of a, we are substituting a, where a is chosen from the x values. PL to show. Okay, let us take this to be some dots, green dot. These are the points. The distance from the points to the curve is the least. That's how maybe if you increase it to degree 3, I don't know what's going to happen. If you increase it to degree 3, somewhere we need to adjust. I don't know where it is. Okay. Constant matrix is, till there it's working. Constant matrix is coefficient matrix. Okay, coefficient matrix inverse needs to be a square matrix. Here we have actually used something specific to here. See, here we have used x power some I, x power some I plus 1, x power some I plus 2, assuming that we need to get a 3 by 3 thing. So here actually we require a little bit more adjusting if you want to use arbitrary k. Okay, this program is not completely general in nature. So this also needs to be actually adjusted. X power some I, x power some I plus 1. Here we are assuming that k to be equal to 3. Okay, that's the problem. So to solve that issue, what should we do? So multiple list comprehensions is going to work. X power I, this is actually a list. This itself is a list. Okay, let me just try to adjust that even. Just attempting. Not very sure whether it will succeed. X power I, x power I plus 1. So I require x power some I plus j, right? It's a square matrix. For j in range k plus 1. Is this going to work? Have we changed the degree to something else? No, we haven't. If we change it to 1, what will happen? It's becoming a straight line. You can see that it's a straight line now. Yeah, if you take it to be 5, it's almost trying to fit. See that? So if you increase the degree, what happens is that the curve will be more and more fitting. But the theory says that if you try to put the degree to be too large, so if you want to get what you call an overall view of the data, where exactly this data is going and what exactly is the behavior of the data. You should not try to get a close view of the curve fitting. You should not try to fit the curve very closely. Okay, you should actually look at the data from a distance. So if you look at the data from a distance, you should not actually use too large degrees. Using is not going to give you useful results. That's what the theory says. Okay, if you want to understand more about what exactly the reason behind this argument, you need to probably refer to some standard textbook on this regression theory, least square curve fitting theory. So anyway, this is how we do the fitting in the case of how we do the polynomial curve fitting with arbitrary degree. Let me update the whole document with this. Yeah, this program is completely general in nature now. I have copied and pasted this to the Google document. You can have a look at all these things. This is a 63 line long, of course, with some gaps in between. So it's somewhat a decent program. We could finally arrive at with all possible generality that we can probably look for. Okay, that's it for the polynomial fit. Now, one more fitting usually is used is exponential fitting. I'm not trying to explain that part basically because once we know how to use, once we understand actually, once we understand how exactly this polynomial fitting is done in Python using the techniques that we have discussed so far, and once we know how to take a logarithm, so exponential fitting is usually what is done is the exponential equation is actually converted. So in the case of exponential equation, exponential curve fitting, what happens is that we need to find a curve y is equal to a into e raised to bx. Okay. So in the case of exponential curve fitting, we need a curve y is equal to a into e raised to bx that fits into our data. So if you require y equal to a into e raised to bx, instead of solving this, instead of trying to fit into this, we need to essentially find a and b here. So to find a and b, we take the logarithm on both sides. If we take natural logarithm on both sides, what happens is we get log y equal to log a plus bx log e. Bx log e is nothing but bx. So now log y is taken to be just taken to be equal to some other variable, say t or capital Y, and in the bx part, So you have bx there. So log, you are therefore trying to fit into a what do you call a straight line. Therefore, you are actually having a straight line kind of thing. Okay, instead of solving the usual thing, you now have logarithmic coefficients there. Now, if you take the anti-logarithm after doing all these things, you will get the coefficients a and b. That's what the logic is. Okay, let me just try share the once again the math world page, which describes exponential curve fitting. So this is what we are trying to do. So we need to fit a function of the form y equal to a into e to the power bx. So if you take logarithm, you get log y is equal to log a plus bx. So essentially, we have some capital Y here. So finally, doing all these computations, all these conversions here and there, finally we get a matrix of this form. Okay, sigma yi, sigma xi yi, sigma xi yi, sigma xi square yi, a b, sigma yi log y, sigma xi yi log y. Now, using this, you need to find the inverse of this matrix once again. Multiply the inverse on left and right so that you will get a and b. But what is a and b? A and b, you just see that b is b itself, but a is this logarithm of a, logarithm of capital A. So to recover capital A back, you need to take exponential e raised to. Okay, we can just try to do that once. Let's try to fit into the exponential curve so that we can completely cover the topics related to all these things. Okay, I will take an example from the textbook that I described yesterday. Okay, so we start the example. Going back to the spider window. So next is problem number 59. So we need x data and y data as before. X data is, I'm taking it from the book Statistical Techniques for Transportation Engineering. Okay, so 1, 2, 3, 4. So the data is taken from that book. Y data is 1.65, 2.7, 4.5, 7.35. So this is the y data that's already given. Now we are trying to fit into an exponential curve. So we need to fit y equal to e to the power ax. This is what essentially we want. Or e to the power ax, sorry, a into e to the power bx, where e is the exponential, usual exponential function. So essentially we need to compute this a and b. Okay. So for computing a and b, what we are going to do is, we apply logarithm on both sides. If we apply logarithm on both sides, we get log y is equal to log a plus bx log e, which is 1. So if we call this to be equal to y, this is equal to a plus bx. This is what essentially we are getting. Now we compute a and b from this. So we already know that this is actually a straight line fitting. Therefore, so we compute a and b from this, and after that we convert this capital A into b back by applying. So logarithm of a is logarithm of small a is capital A. So by taking e to the power, we will get small a. Okay, we can recover small a. So as in the previous case, we need to compute the coefficient matrix. All these things we need to do. Okay, everything is required. So the matrix that we need to compute is sigma yi, sigma xi yi, sigma xi, as in the previous case, sigma xi yi, sigma xi square by a. But what was in the previous example? What do we do? There it was only x to the power sum I plus j. Okay, let us see how to do that. So here we need sigma yi, sigma xi yi, sigma xi yi, sigma xi square y. That's basically because, okay, this is a polynomial, this is a linear thing. Therefore, there is no need to worry about if the xi is up to how much the power of xi will be going. The power of xi will be going only up to 2. Therefore, we don't have to look for any generality. So we can straight away form the matrix. So the coefficient matrix, we are forming that. So the first row will be array. The first row is going to consist of sum of y data, sum y data. Second element is sum xi yi, sum x star y. That is the first row, and the second row is sum xi yi, sum x y, and sum x square y. Oh, sorry. I should have used x data and y data. Instead of that, 1, 2, 3, 4. 1, 2, 3, 4. What's the problem here? 4 and 6. 1, 2, 3, 4. 4 values. 1, 2.7, 4.5, 7.35. Here you have 2. Operands could not be broadcast. 4 and 6. Where is the 6 appearing? Oh, sorry. Okay, we have a 2 by 2 matrix. 16.2, 49, 49, 170. Let me see if it's correct. Oh, I don't know. It's not done exactly like this here. Let me just try to find the right side matrix, which is sigma yi log yi, sigma xi yi log yi. So the constant matrix is NP array. So this is a column matrix. Okay, it's a column matrix. So sum x data star y data xi, sorry, yi log yi. Sorry, this is not correct. Yi, but can we apply log directly? I don't know. NP log should work. Yi log yi. That's the first entry. Second row is xi yi log yi. Printing. Now we need to take the inverse. So after taking the inverse, we get A and B. Capital A and small t. A, B. Or you should not probably take like that. Okay, anyway. Coefficients. So NP inverse of the coefficient matrix into minus 15, 5. Let me just see if it's correct. Okay, let us try to plot it and see if it's working. So A equal to, this is A and B. So take the exponential value for the 0th element to get A. B equal to A and B are minus 15 and 5. So again, plotting as in the previous case. X data and Y data plotted. So Y is equal to AX plus B. That's what we require. So we need to import A star X plus B. So within what range we are taking? 1, 2, 3, 4. Okay, let us take 1, 2, 3, 4 certainty points and unexpected intent. No attributes substitute. For X in X value, X is this, XA. Oh, sorry, maybe it's not because of that. Substitute Y dot substitute, but what is this Y? Y is already taken to be equal to AX plus B, where A is a symbol. So A and B are numbers. A star X plus B. Or AX plus B or A plus BX it is. It's A plus BX, I guess. But that is not going to make much difference. No. Okay, let's try to see print Y. This Y is nothing but what is the last print? Oh, why is it coming like that? Take A, Y is equal to, okay, let me just suppress this. Let me suppress coefficients also. None of these things are not required. 7.847 into X. Why we are getting two values here? Oh, so there is something wrong here. Constant matrix is NP array some Y data. This is one entry. First row, second row, that's fine. What about the okay, I don't know whether the multiplication is giving the correct result or not. We just change it to, instead of dot, let us change it to the coefficient matrix is fine, 16.2, 49.5. Constant matrix is just this. Okay. Oh, sorry. I did not multiply. Okay, that's the problem here. Here, the multiplication is not proper. It will be dot. This is not star. That's why it's giving there. Okay. 16.2. The coefficient matrix A and B. So what are the coefficients here? Coefficients are printed to be coefficients. Okay, let us print even that. 0.014, 4 point. So we need to take the first entry into that. Okay, so coefficients 0 is required. Okay, so that's the mistake. And first 1 0. Now trying to plot once again. Since we have already used A, I'm just changing it to C. I'm seeing this is not in this range 1 to 4. Okay, this is not. Oh, sorry. This is y is equal to a plus bx is not what we want to plot. But instead of that, we have already computed that. So y is equal to a raised to bx. A star np exponential. Now, will this work is another question, because np exponential may give some error. Yeah. np exponential b raised to x. Substitution here is creating some troubles again. So the exponential function, because the problem is that np exponential function, and here we have a symbol. That's the problem. So you need to be really careful about these things. Maybe the symbolic Python thing itself we need to use, not np exponential. Yeah, that seems to be perfect. That's it. I'm updating the Google Sheet. So we have discussed the polynomial curve fitting in the case of a general polynomial, and the exponential fitting also. These two are the two things that we discussed. So I have copied and pasted this into the Google document entirely. Please have a look at that. So if any clarification is required on these things, you may please ask now, so that we can move to the next topic. So curve fitting, what I understand is it's a vast area where you have to understand a lot of things. So I think mainly statistics related areas usually use this curve fitting, essentially because in mathematics we may want to get a function which passes through exactly those points, but in practical sciences and the statistics, most of the times what happens is you get a better understanding of the data. How does it actually look from a distant point of view? The curve fitting is usually used. So I think mainly statistics people may be knowing much about this curve fitting, regression. So the R square kind of fitting. I don't exactly know all these things. I have gone through all these things just for the sake of explaining these things to you. So I don't know much I don't know much about the theory behind this least square and why this least square is actually preferred over any other kind of fitting. All these things are not quite known to me. But whatever I have explained is only from the computational point of view. I explained only those things which are actually required to understand how these techniques are working. Okay, why these techniques are working and for what these techniques are being used is not entirely known to me. Okay, let me frankly say that thing. So for that, you may have to refer some statistics textbook, or maybe some of your colleagues, some of your teachers in statistics may be able to give you a better understanding of these things. So as far as this computational part is regarded, I may be able to clarify certain things. If there is anything required to clarify, I can do that now. Okay, so since we have completed this this curve fitting related thing, now we are going to move into the next topic. The next topic that we had discussed previously was in as per the schedule is basic linear algebra that we yesterday took that portion. Now we know that to find solutions of polynomials or to find solutions of any equation, it's not always possible to find equations exactly. So what do we usually do in the case of approximations? When in the case of practical sciences, physical sciences, we may require an approximate solution only. There are different techniques used for approximating solutions of equations, not necessarily polynomial equations, but even for equations involving trigonometric functions, logarithmic functions, exponential function, etc. So in such a situation, two well-known techniques we can employ, of which one is bisection method and other is Newton-Raphson method. So bisection method is quite straightforward. Newton-Raphson is also. So both these methods essentially uses some. So in some ways, some the continuity of that function is essentially used in some sense. Okay, let me just try to go into the bisection method first. After that, we will try to see the Newton-Raphson method also. So afterwards, the topics left for us is a Gaussian elimination for solving system of equations. We have already seen that numerical Python itself and not numerical Python, symbolic Python actually gives you a way to solve a system of equations. But to understand mathematics properly, we should not actually just look at the solutions, but we need to write programs in such a way that we can understand what exactly is happening. Because the commands available in SciPython, symbolic Python, or numerical Python will be only giving the final solution. But to understand the problem properly, we need to see the intermediate details also, in between details also. For that, we need to write our own program. There is no other way. Say that bisection method actually uses the intermediate value theorem. So the intermediate value theorem essentially says that if you have a continuous function from one interval to another interval, and suppose that we have a value d between f of a and f of b, since we are using continuous function, if you are using a closed and bounded interval, the image is also going to be compact because it's a compact set continuous function. So image is also going to be compact. Therefore, you will be getting a closed and bounded interval once again. So FA and FB, if you have A and B are the right, left and right endpoints of this function of the domain of f. Fa and fb will be the right and left endpoints of the other interval, not necessarily in the same order, but probably in the reverse order. So if there is a d between fa and fb, then we can find a c in a and b such that fc is equal to d. Okay, or otherwise fc minus d is equal to 0. So the bisection theorem essentially makes use of this. So if we have a solution, suppose that we have a solution, then that is between a and b. Okay, if f becomes 0 at some point, a solution is there. A solution is going to be in the interval a and b. But in case of a solution, then we can say that that solution is going to be in one of the subintervals a to a plus b by 2, a plus b by 2 to b. And we will throw away one of the intervals and we will take the interval in which we assume that the solution is going to exist. We keep on going down like that, bisecting the interval again and again, so that the length of the interval become negligible, so that we can make sure that we are very close to, approximately very close to the final solution. So that's essentially the technique is. Okay. So let us try to solve a problem and straight away go into that. Try to solve a polynomial of a large degree. And one thing is that we need to check whether in which interval we need to provide the endpoints of the interval where the solution is going to probably exist. Okay, so let us start. This is problem number 5060. The program is very easy. Suppose let us define the polynomial first of all. Using symbolic Python, I think that's better. Otherwise, we need to provide the coefficients. So providing the coefficients is also fine, but the only thing is that okay, we don't have to provide the. I think it's better to put it as the power using symbolic Python. Otherwise, the thing is that we need to fill all the coefficients. Okay, whenever some coefficients are not existing, we need to fill those with 0. If you are using symbolic Python straight away, we can straight away give the coefficients and use the substitution method. Use y is equal to. I am defining a polynomial after importing symbol x is equal to symbol x. So defining the polynomial, I am taking this example from from the internet, one of the PDF files, so that I can compare whether the solution that we are getting is actually correct or not, instead of trying some random thing. So x to the power 15, x to the power 15 plus 35 x to the power 10 plus 20x cube minus plus 10. This is the polynomial y equal to 0. So this is a polynomial that we have. Let us try to plot to see whether some solutions are existing. So we need x data and y data. Or x points. Let's try to plot in say minus 5, 5. So since x raised to 15 is involved, the number is going to be too large. That's what I'm really wondering, whether it will create some trouble or not. Let us try to plot in minus 5, 5 anyway. Minus 5, 5. Okay, linear space is required. Sorry. Between -5 and 5, say 20 points. Or let us otherwise take it to be a little bit small and take 30 points in this interval. Y points is to be obtained by substitution. Printing to see. Okay, X points are here. Y. Y points are also here. Yeah, as I told, it's large. Okay. Anyway, it's working. So trying to plot to see if a solution is there between -3 and 3, so that we can start with that solution, that interval. It seems to be so because we can see that the curve is actually closing. The curve is actually closing this x-axis so that it's becoming equal to 0. F of x is becoming 0. Okay, at some point. So f of x is equal to 0 means that there x is an x. So solution is there definitely in the interval -3, 3. So graph crosses x-axis. So solution exists. So that is the very first observation we have. So in the bisection method, what next we do is we try to find out, okay, let us call this as AN. AB equal to -3, 3. And use A, B. Now let us bisect this interval and construct a C. So we need to do it in a, we need to do all these things in a loop. We will be doing that after unexpected intent. After trying, after doing the first step, we will put that into a loop. So C is equal to A plus B by 2. Now, what do we need to check is, see, the solution is f of A and f of B. See that the solution is there. Okay. Solution is there in the interval f of A to f of B. No, sorry, not in f of A and f of B, A and B. So, since the solution is there in A and B, solution must be in either in A and C. Of course, it can happen that the solution is C itself. So even in that case, we are taking a closed interval. So solution is going to be in AC or CB. Okay, solution is going to be in AC or CB. Now, since the graph is crossing the x-axis, we know that the sign of y is changing from x to y. You can see here. Have you removed the plot? We haven't. You can see that when the function is starting from -3 and going upwards to +3, it's crossing the y-axis. So the function is changing its sign while moving from A to B. So f of A and f of B are of different signs. Now we are going to check if f of A and f of C are of equal sign. F of A and f of C are of equal sign, same sign. We will remember that f of A and f of B are of different sign. So if f of C and f of A are of equal sign, we will drop f of A and we will assume that the solution is going to be in the interval CB. Okay, we will replace the interval AB with CB. So we will look for the solution in CB. On the other hand, if the sign of f of A and f of C are different, so it means that the solution is going to be in AC. So we will drop the interval CB and we will continue this process. So we need to check the sign of these two. Okay, maybe if you want, we can use a signum function once again, which we have defined previously. So if f of C is equal to 0, there is nothing to do. The solution is already found. So that also we can say. If y dot y subs xc equal to 0, print solution is. C. That's it. So else we need to do something. Else what do we need? We need the signum function. Maybe we can make use of the signum function. Not in the loop, maybe somewhere here. Define SGN of x to be if x less than 0, return -1, else return 1. That's it. If what is it we have to check? Sign of y of A and y of C are the same, or y of C and y of B are the same. Y of C equal to y of A, then drop A. Okay, instead of A, we will push a C to A equal to C. Else B equal to C. Now we continue this process. How do we continue? Again, we compute C is equal to A plus B. Therefore, this part needs to be in a group. This part needs to be in a loop. So, what type of loop? So, we let us determine that until the actual value. So, the actual value is already there. Actual value is actual value means that we need to find a C step that f of C is equal to 0. So it can happen that f of C is not going to become actually equal to 0, but instead of that, f of C may become very small. So let us take the absolute value of f of C. If the absolute value is less than, it's very close to 0, very close to 0 in the sense that it is less than some epsilon, we will stop. Okay. So epsilon equal to 0.05. So what do we do? While absolute value of this y of C is greater than epsilon, we will do all these things. In each and every step, let us try to see this. Uh, what's happening to A, B, and C. Okay, that also we can try to see. Print A equal to B equal to C equal to, and this Y substituted to C also we can see. F of C equal to or Y of C. A, B, C, Y of C. These things we will try to see. But we should do that. Probably here. The danger of using while loop is that there is every chance that the loop may not break, loop may not stop. If you are using a for loop, the good thing is that since you are specifying that how many times it should be executed, the loop is not probably going to be infinite most of the times. It can still happen that it's becoming infinite, but most of the times it's not going to happen like that. But when you are using the while loop, you need to be really careful about, because there is every chance that your condition is not met. Therefore, the loop turns out to be an infinite loop, not exiting, not stopping anywhere. Exactly. As in this case, it's turning out to be an infinite loop. So, what is probably happening? Let us see. Oh, here SGN is not used. So, we need to compare signs. Even that. So, let us look at the problem once again. We have absolute value of y substituted xc is greater than epsilon. So y is substituted with xc. If this is happening, then only the loop will enter into the program will enter into this loop. When this is the y, when we are y is actually the function. When we are substituting y to this c to this x, we are getting the value of the polynomial at c. It's greater than 1. So for us here minus 3 and 3, the value is 0. Minus 3 plus 3 by therefore 0. So if you are putting 0 here, and this calculation is happening, if this is equal to 0, the solution is this. Okay, then we need to stop this loop, break. That's also required. So break means that to stop the loop. The solution is found. So if it is not equal to 0, we are checking for the sign of f of c and f of a. If the sign of f of c and f of a, sign of f of c and f of a are the same, only one is required. So a can be changed. A can be changed to c. Okay, we are dropping a. Okay, after that, yeah, this is missing. We need to do this again. A is equal to c, b equal to c. That's what the loop is not terminated. So after that, we evaluate the c again, because inside the loop c is not evaluated. Okay, let's try once again. Yeah. So the final c is not actually printed. Okay, what is the final c? A final c and the value, because we have broken that, and we are coming out of that. This is the last step. So last step, you are getting y of c to be equal to 0.0087, etc. Maybe we can even plot that. plotting C and y of C in red dot. This is the value. This is the final step. C we are getting to be minus, what is C? C is this minus 2 point something, and we are getting y of C to be equal to 0.08 etc. So we can even print the intervals here. Interval instead of printing A and B. This is the interval we are looking at. We can see the intervals through which we are coming down. So minus 3 we started with. Here 0 is 0. Can that happen? Okay, let me suppress all of the prints. I'm stopping all the prints. So print my points, removed the print from there. Any other print is there? The plotting. Okay, let us see once again. Interval minus 3. Okay, that's fine. Interval minus 3. Y of C is equal to this. Y of C you are getting by substituting y. C is equal to A plus B. But how can that happen? 15, 35 x to the power 10 minus 20 x cube 10. You see, why is it giving it to be equal to 0? A, B, one value is missing from here. C, okay, that should. So these are the intervals through which we are coming down. Not here. Let's go like this. Y of C is 10. Minus 1.5. You can see that the interval is minus 3, minus 3, 0, minus 3, minus 1.5, minus 2.25, minus 1.5. So that every time in every step, one endpoint is changing. Minus 2.5. See, it's each and every step it's bisecting. That's what the bisection method is. So we can make use of the plot to find out that how exactly, where exactly to look for the solution. I'm updating. Updating the Google document with this code. Okay, I have updated. And please have a look at that. I think the feedback link is even today. Is it missing? Anil Kumar sir, if he is there, then So feedback link has to.
It is not there. Okay.
So the feedback link,
Sir, ഒന്ന് വിളിക്കുന്നുണ്ട്.
link is not posted, right?
Okay, in that case, we can put it in tomorrow.
Yeah, I think yesterday also the link is missing.
Yesterday also.
Yeah. Okay. So I'm probably stopping with this the discussion with this. So the the bisection method is now it's completely covered. The problem is covered. Now the Newton-Raphson is remaining. Newton-Raphson is also not very difficult. So tomorrow probably we'll be discussing Newton-Raphson method as well as what you call the Newton-Raphson and
How can we fix the initial points of the interval initially in this bisection method?
so there is no direct method, ma'am. So you need to make a guess, calculated guess probably. So the only thing is that probably you can have a look at the graph, right? So by using, suppose that we use only very few number of, you don't have to plot the graph with too many points. It's not necessary. So if you are trying to plot the graph with too many points, and if your interval is too large, the entire computer may slow down.
Okay.
So just for understanding, if the graph is, hello, can you please somebody else is also speaking. Okay. So if you plot the graph of the function with just say some 5 points, then the plotting is not very difficult, but you can still understand. I think who is this Naju Munnisa? Can you please mute? I think ma'am you can mute her. You should be, I think you should be able to mute her. Okay, so
Naju Minnis, please mute.
I think ma'am you can mute. I think you can. I think you can just place your mouse on her profile thing. That microphone will appear. Microphone and the host can do that. Okay, anyways, yeah, okay. So what I wanted to say is the best thing probably is to do that. So there is no default method for finding the interval in which this is going to be located. So the only thing we can do is that we can enlarge the interval. So we know that if the sign of f of a and f of b are different, definitely that root is going to be there. Okay, okay. Sign of f of a and f of b are different, root is going to be there. But still there is actually one problem. So the function may cross the x-axis more than one times. So f of a and f of b may be having the same sign. That's also possible. Okay, so f of a may be on above the x-axis. It will come down to cross the y-axis. It will again go up and just like the parabola. In the case of the parabola, if we are shifting it downwards, so it will cross the x-axis multiple times. So just by taking some random a and b and by observing the values of f of a and f of b, you cannot make it out. It's not possible. Yes. So you may get f of a and f of b of the same sign, but still the root may be there in a and b.
We have more than one root in that case.
Yeah, that's possible. That's possible. So in such a situation, what you can do is you just plot the graph using very few number of points.
Oh.
But then also you need to be really careful, because if you are choosing just a and b will be simply straight by connected using straight line. That's also not actually. So there is no perfect method for doing any of these things. The only thing is that slightly increase the number of points to say take some 5 points in the beginning, increase it to 10 points, increase it to 20 points, and then you may have to change the interval to something else. That's the only way. There is no other way other than that.
So it is very difficult to find out that initial point.
And see, one more thing is that suppose that you have the constant time. Okay, suppose that you know the constant time. The constant time, suppose that it is negative. So in such a situation, you can put x to be equal to 0, so that you will be getting f of 0 to be equal to that constant time.
Yes.
So you have one value. Now you know the size of that the largest power, and you know that once you know the largest power, if you are increasing the value of x, then the largest power will be dominating the other powers. So you can choose a large value so that the constant time will be overpowered by this largest time. For example, if you have x raised to 5, and if you have just x raised to 5 and x raised to 4, both present, suppose, and 10 is the value, minus 10 is the constant value. So if you are giving x raised to 5 to be equal to some 2 to the power 5 or something like that, it will be dominating the entire thing. So in that case, you will be getting a positive value. So you need to apply your own mind. So you cannot entirely depend on the program to do that. That's what I think.
Okay, I think we can conclude now.
Yeah, feedback from I think you may need to wait and feedback it's already here. Okay, sorry. The feedback form is already here. Let me post it to YouTube also.
Okay.
So tomorrow, most probably we will try to discuss two topics. One is Newton-Raphson, which is not very difficult; it's very simple, and the other one is Gaussian elimination. And Gaussian elimination method because we have seen that a finding solution by taking the inverse of a matrix is not going to be possible if the matrix is not square matrix or the inverse does not exist. So in such a situation, there is no other way other than using Gaussian elimination. So we have to go into that. So we'll try to discuss Gaussian elimination, and if time permits, we will go into the LU decomposition, that lower upper triangular decomposition also we'll try to do. So these three topics, these three problems we will try to take up tomorrow. And if there are any clarifications required, you may please ask now regarding this curve fitting Newton bisection especially. Anyway, thank you very much for your patient listening. You may please ask for clarifications if there are any required.
Okay, I think we can conclude now. Thank you, sir, for your excellent presentation, and thank you all. So we will meet tomorrow at 6 p.m. Okay, once again, thank you all.
Yeah, tomorrow at 6 p.m., right? So the time that I forgot the day before yesterday to remind. So tomorrow at 6 p.m., right? Thank you.
Okay, thank you, sir.